A field is a mathematical structure containing some underlying set, which we'll call F, with two binary operations called addition and multiplication, such that whenever you add two elements from F, you get back an element in F, and whenever you multiply two elements from F, you also get back an element in F. This property is called closure. A field must satisfy a number of properties, which we now list. If we take any three elements A, B, and C, the following must hold. The first property is usually known as associativity of addition, and the second one is associativity of multiplication. And if you take any two elements A and B, the following must hold. A plus B is the same as B plus A, and A times B equals B times A. The first one is called commutativity of addition, and the second one the commutativity of multiplication. And if you take any three elements A, B, C from F, this is true. This is usually called the left distributive law. The next property says that you can always find an element in F, which we are going to call 0, such that if you add it to any other element in F, you get back that element. This element 0 is called the additive identity. There's also an element in F which we'll call 1, such that if you multiply that by A, where A is any element in F, you get back A. And this element is called the multiplicative identity. And the next two properties state that additive inverses and multiplicative inverses exist. For every element A in F, there exists an element in F which we call negative A, such that their sum is 0. And finally, for every A in F, where A is non-zero, there exists an element A superscript minus 1 in F, such that their product is 1. So these are the properties that define a field. And one can easily check that GF2 satisfies all these properties as well, so it's a field. Now we're going to look at a somewhat interesting example. What we are going to look at is the set of numbers of the form A plus B times the square root of 2, where A and B are rational numbers. So this symbol here, Q open square bracket, square root of 2 close bracket, denotes this set. The set of all possible numbers you can form by taking A and B rational, and forming the number A plus B times the square root of 2. If you understand this example, you have pretty much understood the definition of a field. First of all, I need to make sure that if you add any two numbers from this set, you get back a number in this set. And that is not hard to see because if you take any arbitrary numbers from this set, and if you add them, you get A plus C plus B plus D times the square root of 2. A plus C is rational because A and C are rational. B plus D is rational because B and D are rational. So this is in this form here. This is still in our set. Now, what if you multiply these two? Well, if you multiply these two numbers, you can get a number in this form as well. You just have to do a bit more work, and I'm going to be a bit quick here. So I have A times C plus 2BD because we have B times the square root of 2 multiplied by D times the square root of 2, and then we have AD plus BC times the square root of 2. Again, these two things in brackets are rational numbers, and so this again is in our set. Therefore, this set is closed under addition and multiplication. If we now use the fact that the real numbers form a field, then the first 5 properties come for free, because the numbers in this set are also real numbers. So what else do we need to check? We need to check that for every element, there's an additive inverse. In this case, it's not hard to see what the additive inverse of this is. If you take this number here, clearly it's in this set. But if you add these two, you get 0. The hard thing is the multiplicative inverse. So suppose that you have A plus B times the square root of 2 not equal to 0. This means that not both A and B are 0. Now what we want to find is another number such that when we multiply the two together, we get 1. So how exactly do we do that? The details are going to be left as an exercise. What you want to do is first expand this product, and you can already use this formula here to make things easier. And then compare the left-hand side with the right-hand side. Notice that the right-hand side has no multiple of square root of 2. But in the left-hand side, you have something times the square root of 2. So you want that multiple to be 0. And then you compare what remains. What you'll end up with is a system of two equations in two unknowns, namely x and y. And you can solve for x and y in terms of a and b.